huge sea forming between Eurasia, Gondwana, on the eastern coast of Pangaea. That's in terms of geography. In terms of biogeography, for many millions of years it was a belt. It was a tropical belt with a very certain fauna, with reef fauna, which was very uniform across the globe. This was the Tethyan biogeographic term, and it was characterized by these mollusks. Maybe you would certainly think that in the tropics you have reefs, but during the Cretaceous you had these rooted bivalves. It was bivalves that made the reefs. But anyway, one step back. So we are here in Sri Lanka, and maybe some of you are interested, what does this have to do with us? And we really make a step back, some steps. Now we are 300 million years ago in the Carboniferous. Carboniferous was a time of the first big forests. And here you have a situation where Paleotethys was developing. This is this area here. I guess you see it. The first huge sea. And what did we have here? When we're in Austria, usually it's very exciting for people, like an audience like you, to tell some 20 million years ago we have been a tropical sea. But coming here, telling you 20 million years ago it was a tropical sea is very boring because you still have a tropical sea. So I decided I have to find something better. Going back 300 million years, here in Sri Lanka, maybe you see it, we have been on the South Pole. Yeah, you have been very, very far in the south, Gondwana land. So if you had to write a postcard, your address was Gondwana land. And it was Ice Age. This was one of the big glaciations during the Carboniferous. The southern area, the southern hemisphere, had a lot of glaciers. And we, here in this part, we have been part of this glacial area. This is, everybody knows from the tourist prospects today. Maybe this would have been the same thing in the Carboniferous 2 million years ago to attract tourists for skiing. Of course, this is a joke because tectonics changed Earth so strongly that it did not look like this, but at least we have been in this glacial area. So, go further. Some 280 million years, you see that in the south of Paleotethys, there starts something to develop, there starts a new ocean to form. Here in the south, this will be the Tethys in the future. The red circle is always Sri Lanka. Now what is today Turkey and Tibet, this is now going as huge terrains of islands moving to the north. And in the south there develops Neotethys, and this is what I'm talking about all the time. So this old ocean is vanishing, this new one is forming. And now at about 260 million years, this huge land was Pangaea. And the reason why we are sitting here is this continent. Maybe you can't, you think it's so many million years ago, but in terms of Earth science, we can never make a step on the side and say, oh, this is just the past, because we are part of it. So we are always a part of this evolutionary things. And what has it to do with this huge continent? If you have such a huge continental mass, then this is very dry and hot usually. Like Australia today, there's very little chance to get any precipitation on the continent. And in fact, there are models showing that at the time you had a very hot continent. The northern continent had about 40-degree temperature on average, annually. So really hot. We would have been quite cool here. In Sri Lanka it still was very nice, like here in the room about. But in the rest of Pangaea it was really hot. And why is this the reason why we are sitting here? Because at that time all the amphibians had a breakdown because they need water, it was very dry. But our ancestors, reptilians, they had a big advantage because they had amniotic eggs. They were pre-adapted to these conditions. So without this situation, we would not sit here. Just as a side story. Let's move on. Now we are already about 240 million years ago in the Triassic, in the Mesozoic period. This Tethys is widening here. Turkey, Tibet and other islands are moving to the north. They are narrowing this Tethys Ocean. Pangaea is still a very uniform continent. Still in the Triassic, about 220 to 10 million years. Now this new Tethys is in full swing. And what you would have here, there's Salzburg in Austria, and somewhere here is Timor Islands, and you could have hired here a boat to see the coral reefs, because this was a time of enormous coral reefs. The Barrier Reef, in comparison, is something very small. So this was a time of huge coral reefs. Anyway, now we go on. We are already in Jurassic, 200 million years ago. Still, we have this Pangaea situation, but it starts to break up a little bit. Paleotethys is vanishing, and now we have this huge Tethys Ocean going on. Now, during the Jurassic, Pangaea is ending. This huge continent is breaking up, and here in Sri Lanka, you see there's the first breakup of this Gondwana environment, and some of you may know what happens now. During the Jurassic, here we have the first basins in Sri Lanka where continental sandstone is developing. So what is interesting in sandstones? If you go to Taboa, then you will find there beautiful plant fossils. This is one of the big heritages of Sri Lanka, these Jurassic plants with many different genera of different plant fossils, like this Ptilophyllum. It looks like ferns, but they are not really related to ferns. This is what they would have looked like living. It's Benedictinus. It's a completely extinct group of seed plants, very characteristic for Jurassic times. This is really something spectacular. So whoever is responsible for this area, protect it, because it will not grow again. Let's go on. We are now in the Cretaceous already, and now this split up of Pangaea goes on and on. Here you have the Atlantic growing. Here you have the India and Madagascar and Sri Lanka starts to get split off Africa. You have some gravens developing here, shallow seas coming here. Perfect time for tourism, huge shallow lagoons, very nice. Some dinosaurs around, so be careful. It's not leopards, it's dinosaurs. That may be difficult here. Now you already have a complete separation of India and Madagascar and Sri Lanka from Africa. And you find these characteristic ammonites at that time that inhabit these shallow seas. Very nice, ammonites are something like cuttlefish related animals. Now we go on in the Cretaceous. Now India starts to split and goes on its journeys through Tethys, and Sri Lanka is part of it. So it just moves on. So we move now through this ocean to the north. Some 80 million years ago, some 70 million years ago, we are already a big island in Tethys. And now towards the end of Tethys, India was inhabited by numerous dinosaurs. And I'm sure that some of these guys were also present here. Why don't we find them? Because all these Cretaceous sediments are gone. They're eroded. But there's no reason to suggest that they haven't been here. So most probably you had all these creatures here around in Sri Lanka. Some 60 million years ago, there was a big hit. A meteorite came in, an asteroid, killed off most of the fauna of the biota, changed the world dramatically. But in terms of geography, nothing special happened. We are still a part of a huge island moving towards the north. And now we are already in the Eocene, about 50 million years, and this is very important because now India starts to get contact to Eurasia, and suddenly all these alpidic mountain chains start to range, and we have a separation of this western Tethys Ocean, this part which may be the Indian Ocean in some million years, something that will be Indonesia in some million years, so the world changed completely. The current systems change completely. And what happened now? This was the last peak. We all are concerned about global warming. This was the last peak global warming. This was the last global optimum, enormously warm temperatures, and you can find it easily because there was in the shallow seas, there are not much corals, but what you would find is this. These are protists. They are called nummulites of this size, up to this size, unicellular organisms, foraminifera, forming rocks. And they have been everywhere in the shallow seas. So wherever, if you have booked a trip to the sea, then you were standing in the nummulites. Very nice. And just as a side story, the famous pyramids in Egypt, they are made exclusively of nummulites. These guys used these Eocene rocks made of these foraminifera. So now still we're in the Eocene. India already contacted Eurasia, and all these seas start to get narrowed because Africa is moving to the north, everything is moving, and this former Tethys Sea is somehow vanishing. It's narrowing. So here, this was a huge ocean, now it's just this small remnants. And we are here now more or less in a position which is recognizable with this today. About 20 million years now, it's over. Tethys has vanished, and we have the birth of the Indian Ocean, we have the birth of the Mediterranean Sea, and this is the reason why we came here, because now, about 20 million years ago, you have sediments here, witnessing this thing. It's in Jaffna, it's in Aravakula, and these typical limestones can be found here. And there even a paper by a colleague from here who worked on this. And we tried to find this again. And this is the reason why we're here. So we studied the area of Puttalam, Jaffna, Yala, and we tried to find things that fit in this time. Yeah, finally, about 10 million years ago, India is already really strongly pushed towards Eurasia. These are two different oceans. Tethys is completely gone. But what happened now? By this enormous push of India that comes like an elevator, something big happens, really big. The Himalaya, the Tibetan plateau, it rises, it comes up, it's pushed up, and this changes our world completely. So our modern world is mainly pushed by these things. And here I have a nice graph showing this. This is million of years, and this is elevation, and this is how the elevation changed of the Tibetan plateau through time. You see that around 10 million years, it starts to accelerate. And by this enormous rise of this Tibetan plateau, we change our climate. Our modern climate is a result of that. Because by having built up this Tibetan plateau, this Himalayan change, you change the atmospheric circulation. The monsoon is starting. The modern monsoon that you are experiencing every year, or more or less every day, has to do with this. Because suddenly the atmospheric moisture can't go to the continent. It stays in front of this mountain change. Yeah, and now we're in the Holocene. This is as it looks today. And what we are looking at is this part, the Indian Ocean. This is what we are interested so much. And this is huge. It's more than 70 million square kilometers large. That is enormously large. And because we come from Europe, we try to compare things very often with the Mediterranean, with the Black Sea, with the Tethys Sea, which was a vanished sea in our region. And then you see, this is all very small compared to the Indian Ocean. So this is really a big basin. And of course, this is some kind of hotspot. That's the reason why you are concerned about the biota there. And there are papers working on the biodiversity of this region, and this is just a list of things, how many species of mollusks, because I work with mollusks, are known from the various regions. And you see more than 3,300 species of mollusks are described from India and all these regions. So this is a hotspot area. And another colleague was working in New Caledonia in the Pacific, and he calculated that in the entire Indo-West Pacific area, the amount of mollusk species may range between 11,000 and 90,000. We don't know. So it's a task of biologists to get these things known, but it's enormous. This is really a biodiversity hotspot. So, fine. But as a geologist, I ask, so what? Hotspot? Since when? Why is it a hotspot? Why is it so incredibly rich in organisms? And we have more questions to answer. That's the reason why we are here. So we want to know, when exactly did this Tethys Ocean vanish? When exactly was the point that it completely disappeared? How much faunal exchange happened between this later Mediterranean area and this Indian Ocean area? And something to be concerned, where did the modern fauna come from? And you may ask, why should we care? Yeah, there are several answers for this. On the one hand, it's pure science. Science in itself is a value, so we simply want to know it, even if it has no value on a big economical value. But many biologists work with molecular clocks, and this closure of the Tethyan Ocean is used as a marker for biological clock studies. So to know if it is 30, 20, 10 million years makes a big difference for the molecular clock studies. And on the other hand, many people are concerned on ecology and environment. But if you're concerned on environment, you should know what is the original environment. Where does it come from? So there's, for me, many questions. So, and now our starting point. Why did we start to work here? We wanted to know these things. And the starting point was to go to literature. And there are literature data. You see all these dots here. This is all literature. That's beautiful because everything is studied. At least it looks like. So you can go to literature, take out the things, and you can use it for a database. But this means garbage in, garbage out. It didn't work. We tried this, but it didn't work. It's like a monkey just taking information. Why? Because things are enormously old. Sometimes it's 100 years ago that somebody studied. You have numerous misidentifications. Very small samples. Usually it's data from geological reports, and the geologists were not so much interested in the paleontology. So you can't use it. It's simply comparing apples with pears. So the database approach failed completely. We couldn't work on that. And just to show you this debacle, if you look in the Holocene today, there's a good database. Like this OBIS, which is a Ocean Biogeographic Information System. You can get it on the internet. It's free. And then you can see there are about 430 species described in the Atlantic, about 80 in the Black Sea, about 1,000 in the Mediterranean, another 1,000 in the Red Sea. You get increasing diversity in Eastern Africa, in Western India, in the Chinese Sea, and then you have this enormous hotspot in the Philippines and the Indonesian area. This is the modern gastropod species, to say. And now I used my literature data for the early Miocene, let's say 20 million years ago. How does it look like? Here, suddenly you have more than 1,000 species in the Mediterranean, more than 800 in the Atlantic, in the Black Sea, but only 300 here in Western India, only 50 in Eastern Africa, about 300 in Indonesia, and only 25 published species here in Sri Lanka from that time. And this is not very realistic. Of course, there was much more. So this is a pure artifact. Why? Because here, people have been working for 150 years. You have 800 papers at least working on mollusks from there. And in this area, you have a handful. So you can't compare. And there's another problem. You have a filter, which we call taphonomic filter. Taphonomy is just a science which is concerned on how things preserve, how fossils can be preserved. And what is the problem? In these areas where we're working, you have carbonates, limestones. And in limestones, usually all the shells of aragonite are dissolved. So we lose a lot of information. This is a typical aragonitic limestone, and you see all these cavities. All these cavities have been shells, and they are gone. You can't identify them anymore. And there's a very nice paper by a colleague, and he showed how size classes in mollusks are distributed in the Indian Ocean. He shows that most things are small. These are all very small shells, and these are the big things that you collect on the beach are here. But they're just very few in terms of biodiversity. So collecting these things on the beach is nice, but it doesn't tell you anything about biodiversity. That's bad for biologists, but they can go there and try to collect the other thing. For me, this is a very bad information, because dissolution means that all the things are lost. The things that I have at hand is this. So we have a very limited database. That's a fact, and we have to work with it. And another thing is that we all are human. We have a human filter. Because where do we get data from? From geologists, field geologists, mapping geologists. And they go there and they collect big things. They are not looking on tiny, small things. So they grab big casts, but you can't identify them. This is worth nothing. All this is worth nothing. In terms of taxonomy, you can't identify it. So I can't use it. So one of the possibilities to overcome this problem is we use silicone molds. We go into the field and fill these cavities with our silicone, and then we have very nice casts of it. This is a published plate. This is all silicone. But it's very nice to describe, so it's easy to identify. So we can overcome this dissolution. And the good thing is, if we go home with our luggage at customs, nobody will complain because we have just silicone. And it's a very nice fauna. So what was our solution? Resampling. Go there. And this took about 20 years. So what did we do? We started close to home. That's logical somehow to start at home. We started with Greece and Turkey and Egypt. Then we moved on to the Iranian basins. Then we started to work in Oman, in Tanzania, in southern India, northern India. And now we are in a new project, and that's the reason why we are here. This is done, and now we want to go on. And to do Sri Lanka, Garo Hills in northern India, Myanmar. This is the points that we are planning to study during the next 3 years. So now on the map, you recognize what is the idea behind. We want to get an idea of the big thing. What is our problem as natural scientists? Politics, always. Because we have big gaps here. We would like to go to Iraq, we would like to go to Somalia, but obviously these are no countries where you can study easily. So these are no-go areas, and we won't get any information from here. I guess many decades. So, and maybe you will ask, because today we had an interview from newspaper, how do you get the data? And it's really simple. What are we doing? This is the symbol of geologists. It's Latin, mente et maleo, which means brain and hammer. And the hammer is our tool. What does this mean? We go there, we need the rock, of course, the rock and the fossil. If you have the rock, we can do thin sections, which means that you have very thin slided pieces of the rock, and then you can look through. And then you can study everything that is inside with a microscope. This is how it looks like, just some examples. And people who are clever enough to understand these things can reconstruct the environment. They can tell you this was a seagrass environment or whatever. So this really helps. So we need a thin section of the rocks. And we want to know how old things is. And for this, we take samples, wash them, and use these microfossils. Millions of these microfossils, they give us information on the age, also on the paleo-environment. That's the base of things that we do. And what do we want to like to have? Something like this. This is one of our sections in the Qum base in Iran. This is huge. This is 2 kilometers. And here in the beginning, this is a mudflat. Here, there's very shallow marine. Then you start to come to the seagrasses. It's fossil, but based on our information from the fossil, we'll know that this is the environment, the coral reefs, the open marine situation. And what we really like to have, like in Oman, are huge sections like this, where we can do the logging in detail. We can study this in much detail. Then you have this, and then, if we're really lucky, then we compare this with internationally standard schemes on sea level changes. This gives you information on the ages of the things. So this is what we like to have, huge sections. Fine. Or this is just an impression of the Kutch area where I've been. But in some cases, or in many cases where we're studying, we have tropical geology, like here. And this does not allow this approach, because you have a lot of weathering. You all know these red soils. These red soils are our enemy, because it covers everything, and it destroyed everything. So what we can have in these environments are very short, very, very minor sections. This is from our field campaign now. This is Vanapilla sitting here on Jaffna Peninsula, and this was the entire section we got. So it's just 2 meters, which is not a big story. But anyway, now let's see the data. Which data did we have? Where did we start? We started in the Sultanate of Oman. And we collected fossils there, and it was brilliant because we had hundreds of meters of sediments of Oligocene age, of late Oligocene age, of Miocene age, and we collected there everything, and we tried to identify it. Many new species coming out from there, of course, because nobody else ever studied this area. These are echinotherms, by the way. This is just for Gayashan, who is somewhere here. This is how it looks like. These are our sections that we studied. And in some cases, fossils can tell you immediately the environment. We stepped out of the car, and you find these things, these tubes. Today we found it in the Geological Institute. They have the same things. It's not easy to recognize, but for us now we know what it is. If you see this, it's easy. This is a recent one. It's called Kufus. It's a bivalve. It's a boring bivalve. It's huge. It's getting up to 2 meters. And this is a recent one with the daughter of one of my friends, just to show you but if you find this, then you know that you're there, because this thing is actually living in mangroves. So fossils really can help you to immediately know which environment you're stepping in. But anyway, so we have been in Oman, and we tried to compare, what do we see? So we are here, and we compared our data with published things from here, and from here, to see how similar are things. And it turned out that most things are, up to 40% are identical with those in Western Europe, or in Central Europe. Very few, only 20% about here with Northern India, and only 10% are identical with Indonesia at that time. What does it tell us? There was a big biogeographic boundary. Something big happened here. This is completely different than the pattern today. Today, all these things are very similar. Then we went down to Tanzania, did the same thing. We went to Rastipoli. It's a very small spot in the Lindi Bay. This is our entire section. So saying I go there 5 times doesn't help, because that's everything that remained. Everything else is eroded. And what we did, this is our section, so it's not really big. And again, but there are numerous fossils in it, and we tried to compare it. And it came out, this has nothing to do with the Mediterranean. It has nothing to do with India, with Arabia. It has nothing to do with Indonesia. So this is highly endemic at that time. So why? Today, Eastern Africa is simply a part of this big Very strange, so we were surprised. But if you see what is the next relative to this the species we found, then we see that most are somehow related to this Indonesian area, but not really closely. Then we went up there to northern India and included data from Sindh and Balochistan. Sitting here, it was much hotter than here in the Kutch area. Numerous fossils, very nice. And again, we tried the same story. In the Oligocene, we have more than 30% identical with this area. So obviously there was a big connection connecting these things. But this is so close, but no connection, nothing. Only 5% of similarity. And only 1% with Indonesia. So something big dividing was here. If you move to the early Miocene, about 20 million years, things change. Very little communication here, but somehow here starts the communication. So obviously current systems were changing. It's not easy to understand. And then we went to Kerala in southern India. This is the outcrop. It was not very spectacular, and just to show you here, this poor guy, he was very nice. This was his private garden. We asked if we are allowed to dig in his garden. He was slightly astonished, but said, okay, do it. And this is me sitting here in the hole. But from this hole, we had many different species. We described them. There's a seagrass fauna. We found also a very spectacular larger foraminifera. This is one of these larger protozoan unicellular things. That's the same thing that occurs here. So that's a connection to the Jaffna limestone, because this thing is also occurring here. And looking again at the similarities, it turned out this and here, 0. So this was completely closed. Everything was gone. 0 here, nothing. Few similarities to the Indian Ocean. So again, something very peculiar. Again, we had big biogeographic boundaries. And we had used the same data, and I hope I don't bore you too much with this, but that's a Chakar coefficient, which looks on similarities between data sets. And the more similarity, the more black, the less similarity. And you see, this has a high similarity. We have here some similarity, and here's very few, but still there is something. So how did it manage to come here to here? And then we looked at which organisms can cross this boundary. And these are some typical gastropods, which today, if you go here to the mangroves, you will find them crawling around. They are adapted to the mudflats. They can survive harsh conditions. And something that they can fly. They cannot fly actively, but they can fly with birds. So they can disperse. And most gastropods can't do this, but they can be attached to birds, so they can cross here large areas which probably have not been connected at that time. But what is surprising, there is hardly any communication here. And today everything is identical here. So why is this so different? Something big happened here. Because here, what happened, we didn't have any current system that combined these things. And now 3 maps just to show you this. During the Oligocene, before this Tethys closure, we had such a situation. These are the current systems. The blue ones are surface waters. The red ones are deep water currents. You see, you had a big current system going in here to the Indian Ocean. But nothing was there. So nothing could go with it. There were no islands, nothing. It was deep ocean. So all what today is Indonesia, with all the islands, didn't exist. So nothing couldn't come here. Therefore, this was a very peculiar fauna, which had nothing to do with anything there. During this was the equatorial surface. During the middle Miocene, about 10 million years ago, it started to change due to tectonics. Here developed a huge current system which brought a lot of larvae. suddenly the Indian Ocean changed completely its picture, because now there was a big exchange. And today we have still these two big current systems bringing fauna here from the east. And this is the same picture of these Chakar indices of the similarities today. It's completely different. Everything is red here because everything is connected. And here, of course, and there's nothing between, of course. So because now you have these current systems going through. This is a new pattern. It's just 10 million years old. You will say 10 million years is very old, but for us, 10 million years is quite young. So this is how the Indian Ocean did look like about 20 million years ago. We had an Eastern African province, very isolated. You had an Eastern African Arabian province, quite isolated. We had a Western Indian Ocean province where we are sitting now in the moment, quite isolated. And you had a Proto-Polynesian province, strongly isolated. And why was it so isolated? Because at that time, this was land. So you didn't have any through flow. So you need the paleogeography to understand why these things were so different. And for this area, we don't know. And this is where we want to go the next 2 years, because we don't have any information what is here. I don't want to go into detail, but we did this also in a quantitative way. So we had information on nearly 20,000 species of gastropods from the Oligocene to the recent. And just to go through, I don't want really to bore you. This was more for the students from the idea. This goes through time. So the red one is the old one, the blue one is the young and recent one. This is the Mediterranean area, and this is the Indo-Pacific area. And you see both are completely separate. So there was no connection at all. These things didn't have anything to do. But for us, interestingly, in most paleogeographic maps, you always have this connection here. So why is there no connection between in terms of faunas? If there was a sea open, what was the reason? Why didn't they migrate these things? And this is really a problem of most biologists, that they don't understand that geography has nothing to do with biogeography. This list shows you the time from the Oligocene to the Miocene, and all the blue things are the connections between the Mediterranean and the Indian Ocean. So you would expect at that time everything can go through. And in between you had land bridges. How can we recognize land bridges? It's easy. It's especially good, I think during the last days you had some ceremony with elephants, so it has to do with the land bridge. Because during these land bridges, here, and during this land bridge, the first elephants from Africa came to Eurasia. So our elephants here are, of course, the offspring of these elephants. We got the rhinos from Africa coming with these land bridges. And the Eurasian pigs went to Africa via these land bridges. So immediately in the fossil record, you can find these animals. So we know when things were able to migrate. So we know when the migration was possible, and we know when the marine gateways were closed. But looking at the marine faunas, we see that at that time, here we had during these stages, we had a very good connection between the Indian Ocean and the Mediterranean. And here we didn't have. Also, there was a marine connection. So this sounds crazy, but simply think on Southern Africa. Southern Africa obviously is a connection between the Atlantic and the Indian Ocean, but there is hardly any faunal exchange because of current systems. And the same thing happened here. So it's not necessary to separate oceans completely, simply to separate the biota. And this is the thing that we want to tackle. And why is it important? Again, for the molecular clock analysis, because now we know somewhere around 22 million years, things stopped to exchange. And now back to the hotspots. I said here we are in a hotspot. And really we can show how this hotspot came here. It has a history. This is a map based on coral diversity. About 40 million years, the green one is the hotspot. The green is the highest diversity on coral reefs. And you see that in the Western Tethys, in western of Italy today, you had all these coral reefs. This was the highest diversity. During the Miocene, it was slowly moving to the east. And nowadays, of course, we are far in the east, and these hotspots have shifted. We can play the same things with this larger foraminifera, as I told you. It started in the Eocene, the highest diversities in the Mediterranean, and then slowly moving to the east. So you had these diversities moving to here through time. So they are heritage, to say. And what's the driving force? Geodynamics and climate. Because all these islands simply didn't exist before. So all these Indonesian islands were not existing before, where nowadays you have these huge diversities. And the climate, of course, because it's getting cooler. Here in this area, it's not possible to maintain these diversities anymore, because the Mediterranean today is a cool thing, and it was shocked by the ice ages. And some of our Indian Ocean animals that are very typical have a heritage in the West. So this is the shrimpfish that you may know. It's a very typical Indian Ocean animal. But where does it come from? The first fossil record comes somewhere from here, 20 million years ago. So they developed in the West and moved to the east. Or dugong, a very characteristic animal for the Indian Ocean. The oldest records come from the North Sea, so it moved slowly to the east. Or this very characteristic Indus dolphin with this long nose. It's today restricted here to the Ganges and to the Indus, and it had a record that started somewhere here. So these things moved. So the modern Indian Ocean fauna is partly rooted in these western things. And to show you one of the nicest examples, most of you will know this Tritacna. They are protected, they are natural heritage, they are on the red list, and they are emblematic for the Indian Ocean. Where do they come from? In fact, they are French. So they started here some 50 million years ago in the Atlantic, are the oldest records of the ancestors during the Oligocene. They moved slowly into the Mediterranean, then started to settle here, the Oman. During the early Miocene, they got extinct here, but they still survived here and started to spread. During the late Miocene, Pliocene, Pleistocene, and then they spread everywhere. So what you see today, these big Tritacna, the giant clams, are in fact the heritage of this Atlantic distribution. So you have a vector that goes from west to the east. And now, I'm not sure if some people are here working on genetics, but there is a paper working on these clams, and they say, no, that's not true, because our gene data say that our modern tritacnids that we can collect here everywhere were transported from the east to the west, which is contradicting. So how can this be that we say everything comes from the west, and the modern biologists say, no, the modern tritacnids come here from the east? It's easy to explain, but you need geology. During the last glacial maximum, the sea level was very low. And here in this area, this low sea level caused extinction, regional extirpation of these things. And what we see is a re-immigration of these animals coming here from the Indonesian Pacific area, going back. So you see, it's very complex. We have a Western heritage which somehow disappeared, and now it's an Eastern heritage. So I think this is very spectacular to recognize. And one last example, you can also be the dead end here in the Indian Ocean. And one of my favorite animals are the strombids. That's a gastropod group. And there's one genus that is Persistis thrombus, which originated somewhere in the Eocene and lived in the Western Tethys around the Oligocene. And it managed already at that time to invade the Indian Ocean. It survived, of course, in our area, in the Western Tethys. This is from India, so it survived here. Then it managed to, which is quite spectacular, to cross the Atlantic. So from the western Tethys, it managed to go to the Atlantic, to the western Atlantic in the Miocene. It survived in the middle and late Miocene. It still is present here in Indonesia. During the Pliocene, it managed to settle the eastern Atlantic, western African coasts. It still survived in the eastern Pacific and western Atlantic. And today, it's still living on the west coast of Africa. It's still living in the eastern Pacific. But it became extinct here. It became extinct here. So why? What is the reason? If we look, what do these animals need today as temperature, then it's quite easy. Today, they are restricted to tropical areas. They need at least 24 degrees for the larvae. So in the Mediterranean area, they were extinct by the ice ages because it became too cool. But the ice age is not a very good idea to explain why it became extinct here in the Indian Ocean. What happened here? And now we need the biologists again. They did studies on the strombids, and this is just one of these phylogenetic trees, and it shows that during the Pliocene, they started to radiate. That was the heyday of strombids. They got many new genera developed here in the Indian Ocean. And these new genera simply outcompeted these old Tethyan relics. Somehow they were better adapted to these environments, and they got extinct. So you had old Tethyan relics which were extirpated by new Indian Ocean stuff. So you see it's a complete mixture of things. And we are already close to the end. Just some conclusions. So this burst of the Indian Ocean where we can stand on the beach now is twofold. We have a geographic burst. This happened around 80 million years. This was the time when really both the Mediterranean Sea and the Indian Ocean were completely divorced. And in terms of biogeography, it was much more complex because already during Oligocene times, some 30 million years ago, we lost the connectivity because current systems changed and things developed differently. And what's really surprising, this early Indian Ocean was very strongly characterized by provincialism, which is not here today. It was a completely different sea. So if you would have stepped out on your boat 20 million years ago, you would not have recognized your Indian Ocean at that time. In Eastern Africa, the endemism was highest. And the reason simply was that at that time, you didn't have this equatorial current coming from Indonesia, bringing all the larvae, mixing everything. So you were really something separate. And this big geographic diversification in the Indian archipelago and the effective transport of the biota started around 40 million years in the middle Miocene, and then everything homogenized. And by the same event, most of these archaic elements became extinct. And on the other hand, the latest thing that usually biologists are not really aware of, that the Pleistocene sea level changes really shaped our fauna strongly. Why? Here this picture showed this very nicely. If you go down 100 meters in sea level during the Pleistocene, then we have very steep coasts here, but you have here a lot of shelf. Going down 100 meters means that all the shelf is dry land, so nothing can settle here. And this is a reason why you have regional extirpation of things, and then they have to resettle from the east, coming back again. So this was somehow a dead end during the Pleistocene for many shelfal elements. So re-immigration was very strong. We observed this, we know this, but what's still needed is a quantification. And this quantification has to be done by the biologists. They have to gather genetical data to prove these things. So we just are the people to bring the ideas and to force them, but now some geologists are here. It's your turn to do it. And with this, I'm more or less in the end. You should never forget, if you're on the beach, still Tethys is looking at you because you're somehow Tethyan heritage. But I thank you for your audience. Are there any questions? Can I answer anything? It's a mixture. We are not so clever. We use old literature. Because in all these areas, there are geological surveys, people who worked there, who did mapping. But the difficulty is to see which information you can trust and which is just made by mapping. Because the idea of mapping geology is not the same that we have. Sometimes they are pretty happy to fill the maps. And sometimes we need very special information. And the other thing is that sometimes the information is very old. When we started here in Sri Lanka, on some parts of the things where we went, the literature was about 100 years old. It's exactly 100 years. It was 1916 that some English guys went to some of the sections where we went. And of course, road constructions changed things and reforestation, so you never know. But it's not so difficult.
You showed us like these pictures of mollusks from the big area.
Yeah.
Were they all the micro mollusks or were they?
No, it's mixed. The largest one was this size, but many were very small. We had to dig in the garden of this poor guy and had some samples, and you can imagine in these samples you had loads of small things and few large things. This is also the difficulty in comparing things, because some people just collect the large things, and if you just have the small species, then it's very difficult to compare if the biogeographic sense of this, or the meaning of these things.
What was the name of the marine mollusks you showed out of the tubes?
The tubes?
Tubes, yes.
Kufus. Kufus. It's not boring. It's in the sediment. But it's related to boring bivalves. But in this case, it's in the mud. I think it should exist here as well. Today, it's very common in the West Pacific area, but not 2 meters high, probably. This is, for us, it's too much in the east. The Pacific is a different world. So the Galapagos Islands get the fauna from the western coasts of the Americas. So this is really a different world. So we are happy to stick in the small Indian Ocean.
One other question, have you looked at Mantai?
On what?
Mantai.
I'm not Mana. Yeah, we have, there's a, but the Mana Basin is steep, so you can just see the drillings from there. And the surface, you don't see anything. So we went there, but on the surface, you have no chance. But it's an old basin, and it's full with Cretaceous and younger rocks, but it's just for the oil companies. So we have no chance to get information from that. No. You have no chance. Yeah, maybe. You have just a chance for dinosaur fossils in Tabor area where you have Jurassic sandstones. And you have a lot of plants, so it's not excluded that there are dinosaurs as well. But so far I know, nobody ever found them. But
no one has ever found them, but there is a big possibility because
yeah, for sure.
The right sandstones are there and the right age, right?
It's the right age, it's the right sediment, it's the right environment. So there's no reason not to find dinosaurs. But it's a protected park, so maybe the rangers are not really happy with you to collect dinosaurs there.